Hello everyone, I am Mohsen Purveli from Lenovo Research Lab and I am going to present our paper TaxoKnow here. In this paper, we introduce two methods to integrate the hierarchical taxonomy as an explicit regularizer into the loss function of learning algorithm. We wanted to show that by reasoning on a hierarchical taxonomy, a neural network alleviates its output distributions over the classes, allowing conditioning on the upper concepts for a minority class. We limit ourselves to the flat classification. In our first method, we start with the taxonomy, as you can see here at the bottom of the page, in which nodes xi in the leaves is associated with the class labels. We then represent the taxonomy as a symbolic logical sentences for each node, as you can see here. The logical sentence is created by variables and logical connectives. We want to derive a differentiable semantic loss that captures how well a neural network satisfies the constraints on its output. For example, here, sentence DOM.22 states that for a set of indicators x1 to x6, one and exactly one of x3, x4, x5 must be true and the others must be false. And then we transform these sentences into DDNN form, in which two properties, determinism and the composability, as you can see here, makes the inference tractable and differentiable that can be used in a gradient descent fashion, so it can be added to the loss function. And then we used weighted model counting WMC to compute satisfaction of the formula. And finally, we use circuit compilation techniques SDD to compute both the values and the gradient of the semantic loss in time linear to the size of the circuit. A semantic loss is defined as a function of sentences alpha beta in propositional logic, which is defined over variable x and b, as you can see here. A vector of probabilities p for variables x corresponding to the output of the neural network, and a satisfaction vector s for variables b, where b corresponds to the variables of each non-leaf node, as you can see here in the taxonomy tree, to control the conflicts in the different level of the taxonomy. We provided our method in both supervised and semi-supervised manner. In the supervised manner, we assume that all the training data is labeled, and the hierarchical taxonomy is complete, meaning that for labeled class, all the upper parent are known. As you can see, an illustration for supervised semantic loss is shown here, in which iota 1 is the matrix of model output for the batch, iota 2 is the matrix of one-hot vectors over the nodes in the level L2 in the batch, and iota 3 is the matrix of one-hot vectors over nodes in level L3 in the batch, in which bi length and di length should be equal, since the element in one-hot vector bi and di in b is corresponding to sentence delta in d. So in a semi-supervised fashion, we assume that there is unlabeled data and the taxonomy is not complete, and semantic loss is defined only for the unlabeled data. And here, since there are no conflicts between the different levels of the concept in the hierarchical taxonomy, there are no need for a sentence beta over b. As you can see, as an illustration for semi-supervised semantic loss is shown here, and the only difference between this and the supervised is that we only consider unlabeled data in a batch in the different levels. In the second method, our objective is to identify representation for some nodes in the taxonomy given the labels of the other nodes. We consider a hierarchical taxonomy as the labeled graph and seek a GCN encoding of any generally connected node to this graph. Here, in the left side, there is an illustration for two-dimensional GCN encoding of the nodes in a sample taxonomy, as you can see here. We provided a taxonomy backbone graph for each batch, which is consistent across all batches and is generated from the taxonomy. Our method aims to mimic the knowledge distillation approach, where the hierarchical taxonomy serves as the knowledge transfer from a teacher, which is the GCN model here, to the student model, which is the DNN model. And finally, Euclidean distance is measured as the regularization loss to be added to the final training loss. In our experiments, we limit the taxonomy to 3 levels to prevent the task from becoming fine-grained classification. For the data, we use 4 datasets in 2 different languages, Chinese and English. And while a symbolic method show a superior result, in particular in the accuracy of the learner, The GCN method actually outperforms in terms of the macro average, F1 score. And our observations highlight two key takeaways. First, the symbolic-based approach exhibits a scalability for the larger hierarchical taxonomies, showcasing its potential for handling more extensive taxonomic structures. Second, the GCN-based method proves to be particularly effective in addressing long-tail problems, showcasing its utility in scenarios with imbalanced data distribution. Thank you very much for your attention.